So with that, I would like to welcome you one more time to our seminar series, Josh. I'm replacing Pablo today, so we haven't coordinated all details in advance, but I know that it's a very promising talk. You're trying to build up an open source MRI to do research that otherwise couldn't be done in Paraguay locally. And we are really looking forward to hearing from you about this.
That's great, Tobias. Yeah, that's just a brief introduction, because I realized I didn't include much about myself on my slides, but I'm a professor of engineering at the Universidad Paraguayo Alemana in Asuncion, Paraguay. And our university is mostly focused on things like industrial and civil engineering. So I really come to this project with the view of how to build things better. And I think that'll come through on the slides today. So I wouldn't necessarily call myself an MR expert, but I think that's sort of the beauty of this project, is that it's got a place for a lot of different kinds of people. So I'm looking forward to getting started. I should bring the slides up, yeah?
But that looks perfect.
Okay, great. So globally accessible neuroimaging is the goal. And hopefully this is one small step in that direction. Thanks so much to Tobias and LIBREhub for giving me this opportunity to talk about this work. And basically today I want to provide some motivation, or at least my motivation for doing this work. And I want to give a real practical perspective on what it takes to build one of these open source scanners, with the hope that whoever is listening can sort of assess your own resources in your own team and decide whether it's a project you might want to take on, in the future. And then I'll talk a little bit about what we're doing in Paraguay with our collaborators as well, and give a suggestion for some future directions that I think would be interesting for the region, if not for the world. And I just wanted to point out the image of the scanner that you see is one that we did in Embarara University with my good friend and colleague Jones back in 2022. And it's just a beautiful scanner, so I thought I would include it. So why are we doing this? I think I like to start with a very broad perspective, and this is a map of the global burden of disease. It doesn't get much more broad than that. But what you notice is that most of the disease that we see in the world, based on this 2019 survey, is in low and middle income countries. And why is that a problem? Because when you start looking at the health technologies that exist in the world in terms of its density, especially MRI or CT imaging, which are important diagnostic technologies, those very regions of the world are the ones that really lack the resources. So we've got the disease on the one side that's higher, and then we've got the resources that are much lower. And yet that creates a big rift in the treatment care pathway. And we know a little bit about why the technology fails. There's been lots of good work on that question. Some of it's cost, some of it are spare parts, consumables, training, sort of the logical things that you might consider to be a problem in resource restricted areas. But I also think that these quotes from a few scientists and journalists are very interesting, that point out that most technologies are not manufactured in low or middle income countries, only 13%, according to this particular researcher interviewed on NPR. And that creates an issue, because when you don't build something in a country, you lose that intimate knowledge of how it's supposed to work. And that makes it difficult to sustain. And then also, according to a prominent Nigerian doctor, the technologies aren't developed with scientists and experts from low and middle income countries in mind, and they don't always take into account the particular health needs of those low and middle income countries. So what happens is technologies are often developed in high income countries, and then they're donated or sold to the lower middle income countries, and they don't last very long because they just aren't appropriate for that setting. So that's sort of in that spirit. The Sustainable MRI Lab that I run out of UPA is focused on the technology that's missing. So we're going to talk mostly about the technology today. But then we also want to incorporate how we use that technology. So image processing, for example, how are the diagnostics going to be done? and how do we integrate the technology into the workflow of the existing medical system. And that's the focus of our work here. But of course, today we're going to specifically talk about the technology side. So if you're interested in seeing what we're doing, smrilab.com is where we have a kind of clunky but okay website. So what does it take to build the OSI2ONE MRI? Now, if you're not familiar, there's an open source imaging initiative, which is this OSI² part. They chose to square the eye instead of multiplying it twice, I guess. And they released recently this OSI2ONE MRI system, which is a head-only low-field MRI scanner with a center field of about 50 millitesla. And we've reproduced several of these across the world. The mother system, I would call it, is at Leiden University Medical System, and I just have to give some quick credit to Tom O'Reilly and Andrew Webb out at LUMC, because they're really the initiators of this design and the real drivers behind this technology. And Tom's just got some beautiful images coming out of his system. I think the ones on the screen here are even a bit old. So it's just incredible work. These images are only filtered for noise with a low pass filter, nothing special, no artificial intelligence. So it's an incredible amount of definition that he's got in these images. And the system overview, it's an MRI system just like any other in many senses. So we've got radio frequency amplifier, spectrometer, gradient amplifier driving the electronics here. There's 25 acrylic rings that are CNC cut, and each ring has a number of 12 millimeter neodymium boron magnets. In all, there's over 4,000 magnets in the system. So this is a bit tedious and a bit time consuming to build, which we'll talk about that in a minute. But if you have a little patience, just about anybody can get through that part. There is a passive shim system, which I won't cover today. It's the single remaining system that we have to build in our particular system in Paraguay. But we are able to shim a lot of the non-uniformity in the field out using this passive shim system. We've got X, Y, and Z gradient coils that get integrated inside the bore. And there's space for a 25 centimeter head coil, which is just about big enough for head imaging. Not a lot of space for people who are claustrophobic, but there's some real design concerns if you try to make the bore much larger. And then of course we've got radio frequency shielding that we use. That's important to point out, I suppose, now, because there's a lot of systems that use sort of artificial intelligence to remove noise automatically. We're not doing that at the moment. We just use the old-fashioned shielding because it seems to be fairly robust. So I like to think of building this system as a series of processes. And process one is the worst. It's logistics. Nobody wants to think about logistics, but you have to get it right if you want to have a successful build. So in terms of logistics, you have to really think about where you're going to get your parts from. If you're in the US or Europe or other highly industrialized places, it might not be as difficult. But I know from my experience in Uganda and also in Paraguay, it can be a real struggle to import components into the country. And actually, it can even be a showstopper if you don't have people who know what's going on with the importation laws. So in Uganda, when we built the system there, we had a limited amount of time. Tom and Wouter, you can see Wouter there with Tom, and I traveled to Uganda to work with our colleagues there on building the system because we wanted to do it quickly. So it was sort of all hands on deck. And in order to improve the speed of the process, Tom and Wouter assembled all of the components that were necessary to build the system down to the screwdrivers that we would need. And they put them all into a crate and shipped them to the lab in Uganda. And when we got there, we had everything we need. We laid it out. We worked with an excellent team at Mbarara University of Science and Technology to build the system in about 12 days, which was pretty fantastic and really fast. In Paraguay, we took a different approach because we weren't on such a time limited schedule. And we decided that we would ship the CNC milled plastic and the magnets and a couple of other hard to get components like brass threaded rods to Paraguay directly from Leiden, because we already knew that we had vendors that could supply these to spec and with quality. So we shipped those components, and then we imported the rest of the electronics that we would need. And then we worked with local resources to purchase hardware to do 3D printing, laser cutting, other more minor jobs. And it was difficult to find all of the things that we needed, even in a place like Paraguay, which does have a fair amount of resources for building things. It's just not quite as specific as you might expect. So you really have to figure out where your resources are ahead of time and make sure that you have access to everything before you start the build. The first fun process that you do is building the magnet, which I thoroughly enjoyed I have a background in mechanical engineering, so this was very fun for me. And it all starts with one magnet. So you pick one very lucky magnet and you mark the pole north and south. It doesn't really matter which one is which as long as you stay consistent. And this magnet you encase in plastic, and it will be your reference magnet for the entire build. And then you use that magnet to mark all the other magnets, and you can see that you do come across the occasional poorly behaved magnet which gets stuck in the sospechosos box for later review. And then you go filling the rings with magnets. So here we have one of the end rings, which has 3 rows for magnets. And each of those little slots for the magnet is cut with a precision of 0.1 millimeters with a CNC mill. And this is really not a tolerance that's terribly difficult to keep, but it does need to be kept because small deviations in tolerance will really destroy the homogeneity of the magnetic field, which is one of the reasons why we stuck with our supplier in the Netherlands. So here we see a partially filled ring. After the ring is completely filled, we have this somewhat difficult process whereby we need to cover the magnets with another thin plastic layer so that the magnets don't move during construction or during operation. So we apply some special acrylic glue to the face of the magnets, and we glue on thin 2 millimeter thick laser cut acrylic onto that face. And it's quite difficult to do this without making a mess or without having bubbles left in the glue, which I'm demonstrating here. This does hold well enough, but it's a process that we don't particularly like very much. So it's something that you need to practice a lot. After you have your rings glued, so this is the center, the very center ring, we attach brass threaded rods all around. So there's 24 rods in total. And we attach those with brass washers and nuts and get them perfectly centered because we'll be filling rings both to the right and to the left. And then we went inverted with our system so that we could put the rings on more easily to begin with. You slide rings down these brass rods and you fix them with more washers and nuts. And we use specially designed tool and calipers to position them within 0.1 or 0.05 millimeters tolerance based on whichever spec they have. So this one was a 20 millimeter distance ring. And we have to do this caliper measurement at every single brass rod that we have along the ring. So this is also another tedious and time-consuming process, but we know it works. We're able to produce good quality from this method. And then you just keep adding rings to the system. It's very exciting because the magnetic field plays tricks with your minds. Sometimes it pushes, sometimes it pulls, which is a lot of fun. And eventually you have a full magnet built and it looks very beautiful like this one. And depending on how much personnel and time you have, you could do this in probably between a week to a month and a half if you work steadily. So this is a good time if you have undergraduate students or technically inclined people who would like to be involved, but maybe they don't have so much experience. This is a great moment to include those types of individuals in the project and sort of pick out folks who will go on to the next processes and really help with the more technical stuff. So this is our magnet after we put all of the rings together. In conjunction with that process, you can start working on the gradient system. For the gradient system, you need a decently sized 3D printer. So our 3D printer was an Ender 5 Plus, which is about $800, and we were able to purchase it locally, which is why we went with this one. And in terms of quality, it was able to produce the quality that we were looking for. The build volume is not quite as large as we would like, but we were able to adjust some of the designs. For example, we would cut them in two and then glue them back together later to make this system work. Another important use that we got out of this printer is that you must map the magnetic field eventually with a 3D positioning robot. And there's been some great designs of these that I've seen, one by the open source imaging initiative called the Cozy Measure, which I believe they're working on new versions of this. What we did is to save a little on cost, we decided to trick this 3D printer into also being our measuring robot, which we're just now finishing up those field maps, so I haven't included it in this talk, but it seems to have worked, and we will release those designs as well once we've tweaked a few things. And it's good to start the process of printing because it's about a month of printing hours, more or less. So we should start it while we're building the magnet. The main drivers of this this month-long printing is the X, Y, and Z gradients. Both have 4 large pieces. They're quite tall pieces actually, and each one of those takes about 4 days to print for us. So this is quite a dramatic amount of printing that must be done. And then there are some other pieces that need to be printed as well, but the printing the gradients takes quite a long time. And this is a particular issue because of power instability. So if you're printing anything in many of the low and middle income countries of the world, you run into lots of issues with power outages, especially when it storms. So we would be several days into a print and then the power would go out, and our printer actually does remember where it stopped if the power goes out. But what happens is it pauses, and if it pauses for a long time, the print head is still hot and it sort of sticks to the part, and then when it starts again it moves the part, or it has a clog, or it was just sort of a disaster every time the power went out. So we needed a lot more time, and this is probably a quarter of the failed prints that we ended up dealing with. But eventually we did get it right. And so it can be done. It's a little bit of a learning curve if you're not familiar with printing. But in the end, we were able to produce the kind of quality that we needed. Once you do have the coils printed, the gradient coils, we have to do a little bit of rework on the wireways. Because of the way the 3D printing works, some of the edges end up being jagged depending on which plane they were printed in. So we use some sanding tools and some cutters to rework those wireways. And we end up gluing in using la gotita, which is a very common superglue. We end up gluing in the wires into these wireways, and this is AWG14 wire that we used. And when I say we, I mostly mean Rodney, whose face you can't see here, who is my colleague here at UPA and has just been excellent on this project, Rodney Rojas. After we wire all the gradients, we have to get them inside the coil. So here we have sort of a brilliantly designed way of putting these gradients in. They overlay each other and snap into place inside the coil. And then the very last gradient, which was the X gradient, just about slides in with a little bit of difficulty. And here actually I see the photo I've taken here is before I fixed it. These two pieces were actually overlapping. They don't in fact do that anymore, but this was a challenge of getting this gradient into place because they fit just perfectly. But this is the process of sliding the gradients in. Once we have the gradients in place, we cut some 30 micrometer copper foil because we need a shield between the gradients and what will be the radio frequency coil eventually. we've discovered that the gradient amplifier introduces a little noise into the gradient coils during operation. And so if we shield between the gradients and the RF coil, we can get rid of most of that noise. So we hand cut these sheets of copper foil and solder them in to place. And then we have a little shield between our gradients and the space that will eventually hold our radio frequency coil. In terms of electronics, I'm using a very nice spectrometer made by Magritech, which is the Kia 2. And I will say that this whole talk is based on wanting to do the best imaging that you possibly can with this open source system. The spectrometer is really the cost driver. But if you want to do clinical imaging eventually, I think it's pretty essential that you pick a really good spectrometer at this stage. There's some other open source versions of the spectrometer which are really great, and I plan to try out. There's one that uses a red pitaya that I'm really looking forward to trying. But we know that the SNR from these types of systems is about as good as it can get. So I've chosen to go with this spectrometer and sacrifice a little bit of cost. But there are lower cost ways of doing this. And I use a Bartel 3-channel gradient amplifier for the same reasons. I don't want to skimp on the electronics because I want the best chance possible to have good clinical imaging eventually. So moving on to the radio frequency system, we've 3D printed a 20 centimeter, actually I think it may be 15 centimeter coil form, which is appropriate for knee imaging. And actually, before I tuned and matched this coil, I made my own 5 centimeter coil because it's easier to start small. So first I printed a 5 centimeter coil and tuned and matched that and got that working. And then I moved to this larger coil very quickly. The next day I was able to move to this coil. And so this one has about 24 turns. I've used 1 millimeter solid copper wire, and it's segmented in 3 places to avoid self-resonance near my resonant frequency. This is another potential cost driver, is the VNA that you choose. So we've got this Chelegance portable VNA, which was around $1,000, I believe. And it actually does quite a nice job. I really like it. We were able to tune and match without much issue here with this VNA. So this is what I've used to do all the tuning and matching for my coils. Oops. And then of course we're still using the Magritech as our spectrometer, and we've got this custom radio frequency amplifier, which is part of the open source imaging community. And it was developed by Herman Flick with Tom O'Reilly at Leiden University Medical Center. And it works just fine for us. So the first place that we go when it comes to imaging is a spin echo. And here I've got my knee coil, my 15 centimeter coil. I've got a water phantom inside of this Tupperware because I'm nervous that my water could leak out. And I want to make sure it stays contained. And I was just amazed at how quickly I was able to get a spin echo from this system using the Magritech spectrometer. So this is quite a nice spin echo. This is an unshimmed magnetic field, so we don't expect it to be the frequency to be quite a tight line like we want it to be in the future. Of course, you can see that I've grounded my shield, which is really important for noise, so I need to ground that to the same ground as my RF ground. And these are the spin echo imaging parameters that I used. Just a single scan, so I don't have to worry about my repetition time. But for water, it is quite long, and every day that I show Tom my data, he tells me that I need to switch to an oil phantom, which has a much faster repetition time, and I completely agree with him. So these are the results as they stand now. We do have the capability of doing some imaging with our gradients, but we haven't optimized the gradient efficiency. We haven't shimmed, so our images don't look very impressive at all, just kind of blurs of white. And like I said, we're working on the field mapping and developing the shim system right now. in the next few weeks, we do hope to be imaging with a little more clarity. So if you're thinking about building the OSI2ONE system, where do you start? I think it's very important to keep in mind all the equipment that you absolutely will need. So in terms of fabrication, you're going to need to be able to CNC plastic to a tolerance of 0.1 millimeters, which is not that difficult, but it is a good tolerance. Not just anybody could go do that type of tolerancing. So you need to be working with people who know what they're doing in the CNCing world. This may mean buying the rings already machined from an external supplier if you don't have anybody at your university who can do that, but it's absolutely essential. You need to be 3D printing at the level of the Ender 5 Pro, which is probably a mid-tier 3D printer. It's certainly not the best, but not the worst. Eventually, you'll need to be able to laser cut up to 6 millimeter thick acrylic. So the thickness of the cutting has to do with the power of the laser that you have. If your laser isn't very powerful, as you start getting towards the bottom of the plastic, the laser beam will start to bend and you'll lose your tolerance on the laser cutting as well. So you need to make sure you have that capability. And you need sort of Fab Lab-esque tools. So you need to have screwdrivers, you need cutters, you need drills. A drill press is very useful, though not necessarily absolutely necessary. You need those types of tools and some very nice calipers, because you do have to use calipers quite a bit. And it's really no good if your calipers are not trustworthy, because you also won't be able to put the system together correctly. On the electronics side, you do need a vector network analyzer. So the Chelegans one that we have works fine, and I would suggest using that if you don't have access to a nicer one. You need a magnetometer for magnetic fields measurement. We use the AlphaLab GM2, and it seems to do an okay job. It's sort of at the low end of the magnetometer world, but it does well enough. Multimeter, LCR meter is useful, but I don't have one, and it's been okay so far. And you need a nice soldering station. You do quite a bit of soldering, and I think it's really helpful to have nice tools when you need a job to come out well. So what resources do you need? Start with funding. If you want to buy a Magritech and Bartel amplifiers, if you want to get the top of the line type electronics to have the best chance at high SNR, I would say you need to budget between $80,000 and $100,000 to start off with. It's a conservative estimate, but it's quite easy to spend that much, especially if you don't know how much you're going to pay in import fees, which can be very high. I think we've paid quite a bit in importing electronics here. So that's something to really check in advance. If you do choose to go with the Red Pitaya spectrometer, that drops down to a few $1,000s, I think, but you do have to buy a few extra electronics. So maybe you go from $30,000 spectrometer system to $4,000 or $5,000 in the end after the other additional things you need to buy. There are probably some open source gradient amplifier designs that could also be used in this system if you match the specs to the Bartel that we're using. And the radio frequency amplifier, you can use the open source version as well, which instead of 5,000 probably runs closer to 1,000. So there are much more affordable ways to do this, but again, I give the highest cost estimate because it also is the one that's most likely to produce high SNR. In terms of human resources, I think this is absolutely essential. You can't do this project alone. I would recommend you have somebody with expertise in fabrication, somebody with expertise in electronics, and somebody who knows their way around MR physics. And then, of course, all of those people need to be leading a team of wrench turners who have the time to do a lot of work. There are very few people who embody all of these things at once, and I think it's really better to think of how you can work in a group with these types of people. And I would suspect that you need between 3 and 12 months to build a system, depending on the number of people that you have and the level of experience they have with these types of systems. So you also need administrative support. There's lots of purchasing to be done. If you're in a country like Paraguay, who maybe isn't as used to importing these types of electronics, it can be difficult to navigate how to bring this technology into the existing system, which we've struggled with as well. So it's nice to have people who understand how to do that already on board on your team. And you need to know if there are any country-specific laws that you can use for education, for example, to relieve some of that tax burden. We were able to use some laws here that promote educational technologies and saved us a lot on our budget. But you need somebody who knows how to navigate that system as well. So make sure you have some administrative support lined up. And then, of course, the open source community. I think this is one of the most key resources. There's a lot of people that are very active in open source imaging. You can go to this website and you'll find resources on how to get connected to the Matrix page for open source imaging. People are talking constantly on Matrix about how to improve every aspect of the system. And you can learn a lot, and then you can also engage and share your knowledge with people, which is a great way to start. And of course, this is driven by the vision. He wouldn't claim it this way, but by Lucas Winter, who I think is really one of the first drivers, and now he's passed on to Martin as well. And these guys are just really great to work with. I've greatly enjoyed myself with them. So in Paraguay, what are we doing? Well, let's go back to one of our big maps. And our research with this particular system will be focused on dementia. And this is from a recent paper that shows the predicted increase in dementia over the next 20 years by percent. And you can see, if you think back to the map of clinical imaging technologies as well, the places where we're expecting dementia to grow are places that don't have imaging. And so what we're working on, funded by our friends at the United Consortium, Dr. Adams and Tavia Evans, we're working on building this MRI to send to our collaborator, Dr. Eric Gonzalez, at the Medical Center Neurocenter in Santa Cruz, Bolivia, where they will do an imaging study with the low field MRI system and a high field MRI system to do some comparative image analysis on the types of things that we can see for dementia patients between the two imaging modalities. So this will be sort of a first of its kind, I think, certainly in Latin America. And we're really looking forward to finishing the build in Paraguay so that we can figure out how to send this device to Bolivia and get it installed in their center. So looking to the future, what can we do with these types of systems? I think there's a lot of things that we can do, but the things that are first on my mind are being able to look at brain volume measurements for dementia. So this is not necessarily an ambitious target, but it's something that could be quite useful. Looking at normative growth curves that we can compare in malnutrition. So when kids are malnourished, how are their brains growing and what do we compare that to? I think there's not a whole lot of information on what a normal brain growth might look like for a child in South America versus Africa versus Europe versus Asia. Stroke diagnostics is something that's very popular with the commercial Hyperfine system. There's a lot of work coming out of Yale related to stroke diagnostics. And this is probably a good future application for this device as well as we increase in our imaging capabilities. Trauma, brain trauma, especially from automotive or accidents in motorcycles, is a big problem in low and middle income countries, if not all over the world. And this is something that technology like this, I think, could work well with. Sports industry injuries, scientific discovery. And then one of my favorites, which is training, which is why I've included a picture of some of my students helping to build the system. And I think that the act of building one of these scanners in places like UPA, where we normally wouldn't have projects at this scale, is such a great training opportunity for young engineers or young imaging scientists that in and of itself is really worth it. So the increased knowledge that comes from being able to participate in something like this has a lot of value for the future, I believe. So these are my perspectives on where we can go with this technology as we grow. So before I end, just want to say thank you to LIBREhub and Pablo for inviting me to come do this talk. Rodney Rojas, my colleague here at UPA, who's helped me. Without him, couldn't have built any of this system, I don't think. And of course, my dedicated students as well and colleagues. United Consortium, who helped me to fund this project, Hiab especially, who really kind of made it all happen. Tom, Walter, and Andrew, developing the technology. Lucas, my mentor, Steve Schiff, and Jonas Obongoloch and his MUST team, who have really kept us going on this project for a long time. So that's all I have, and I really appreciate it. I don't know if there's time for questions, but happy to take any if there are any.
Thank you so much for a really interesting talk and insight into your work. I'm really glad this is going on in the region. I'm glad you're in touch, and now even more people know about it and just the seminar. Thank you very much, and yeah, I'm sure we'll hear from each other in the future.
Great.
Good luck with your project.
So much. Thanks, everyone. Bye.